Yeah, hello. Am I audible? Hello. And it's 7 now. We'll wait for a few more minutes and then start. Okay. Uh, yeah, it's 7:05 now, so let us start. Yeah. Hello everyone, I am Suchit, a PhD scholar at IIT Delhi, working with Manik Verma and Sumit Agarwal on extreme classification. Okay, so the plan for today is same as what we do every week. We'll start by revising whatever was covered in the video lectures for this week, then move on to solving questions, and then do some live demonstration coding work. So last in the last class, so we had started doing topic modeling. So we'll finish off that before moving on to autoencoder. Okay, so this is for the coding part. Yeah. So so today I think it's just four of us. So yeah, it's better like yeah, make use of this session, and yeah, I'd appreciate if it's more interactive. Yeah. Okay. So before we begin, can you all introduce yourself to me? I will start with R.S. Yadav. Can you tell me about yourself, what you're doing, and why have you taken this course? Yadav? Okay. Neeraj, do you want to go ahead and introduce yourself?
Maybe hi. Hi Suchit, my name is Neeraj
Hi,
and
Neeraj.
I'm currently studying bioengineering. And I have done deep learning in bits and pieces, but I never had a chance to go through a proper course. So that's why I'm doing deep learning over here.
Okay. So are you using deep learning in your project or somewhere?
Yes.
Okay. So how are you using it in bioengineering? Can you
Uh,
elaborate a little?
okay. So I have used it previously in like we had something called fMRI where we have these bold oxygen signals in the
Okay.
brain regions. So we were trying to predict which brain region would have a stimuli when we show certain tasks to that.
So
So
okay.
in that,
So okay for so what is this basically? This is a classification task, right? So you take the signals and then you predict based on that.
not not classification, more of regression because so let's say your brain is divided into multiple regions, right?
Mm-hmm.
So if you give a task, it is not necessary that only one brain region would be activated. So
Okay.
we have clustered brain region into more, uh, what should I say? Not exactly very fine details, but yeah. So it's more of a regression because bold signals have these values. So we try to
So what
predict the
is
value.
the final task that you are trying to solve?
So trying to understand the connectivity in the brain. So
Okay.
if region one is being activated, which all other regions would also be activated.
Okay. Okay. So it falls, I think it falls under unsupervised learning or something. So you don't have any ground truth
No,
for
but
it.
no, we have ground since. Do you know about fMRI? Do you have?
No, I have not worked on it.
Okay,
Yeah.
so in simple terms, in fMRI, you show a certain task, and then the corresponding bold signal. Those are basically oxygen signals that you can
Mm.
find. So it's sort of supervised learning only, since you have the task as well as the bold readings.
Okay. Okay, fine. Yeah, thank you, Neeraj. Manikanta, can you introduce yourself? Okay, let's start then. So can anyone go ahead and tell me ki what was covered this week in the video lectures. Okay, so no one went through the video lectures or what? Fine.
So this week we went through autoencoders,
Mm-hmm.
and we sort of see that how does autoencoders involve encoder and decoder. You find a latent space,
Mm-hmm.
and how do you relate autoencoders with PCA and
PCA.
certain and various different regularization techniques that people use in autoencoders. I
Mm-hmm.
don't exactly remember the name, but yeah, this was the overall gist.
Yeah, okay, fine. So is my screen visible?
Yep, it is visible.
Fine, yeah. So we looked at autoencoders this week. Okay, so we started with how so we saw autoencoders and then how found the relation between autoencoder and PCA. So we could use autoencoders and come with the same representation that PCA gives us. Okay, and then looked at regularization in autoencoders, and that gave us sparse encoders and then contractive autoencoders. Okay, so let's go through the slides. Okay, first. Okay, so this is the diagram of autoencoder. Okay, so there are two weights W and uh, W star. So Xi is the input representation. From that, we compute a hidden representation and try to again reconstruct the input. So this is an autoencoder, and the H can be used as latent representation uh, of X, the input. Okay. So one use case of this is dimensionality reduction. So PCA is one way, and this could also be this could be other way. So in PCA, we just consider only linear interactions. So here we can, because we are using nonlinearity as well, so we can learn a complex representation over here. Okay, so but if we remove the non-linearity, so this would also end up learning the same representation as PCA, and yeah, we'll get the eigenvalues of XX transpose, the covariance matrix that we saw in the PCA. Okay, so this is the equation to compute the hidden representation and then the final, and this final function f depends on the task. Okay. So if the dimension of the hidden representation, so then we saw different types of autoencoders depending on the dimension of h and the input. Okay, so if dimension of h is less than dimension of xi, it's called undercomplete autoencoder, and if it's greater, then it's called overcomplete. Okay, so what could happen in overcomplete is that uh, the network just copies the weights directly and then outputs it. So it's not learning anything. So there are various ways to solve this issue through regularization that we saw. Uh, in the lecture. Okay. So yeah, overcomplete. And loss function depends on the task. Suppose the input is binary, then the final f function would be sigmoid. Okay. And then we'll train this network with binary cross entropy loss. And if it's continuous, we could directly use MSE, mean square error loss. And f, we could use tan H as it could just be a linear function. Yeah, so then we looked at the backward pass through this model. Okay. So I think in the lecture only the last, so these computation could be ours would be same as what we did in the neural network lecture. So we just computed this with respect to the hidden layer for different losses that we saw. Okay, and then we saw a link between PCA and autoencoders. And there was this proof where if we use this loss function, which is MSE loss function, and remove the nonlinearity, we'll end up learning the H would be, so the hidden representation H would be just X into the V matrix that we get in the SVD of the matrix X. So this was proved in the class. Okay. So yeah, we'll end up with the same uh, representation that we'll get with PCA. Okay, so then we saw different regularization techniques. One was using L2 normalization. Okay. And then there was wait time where so same wait W is used for computing the hidden representation and then from hidden to output. Okay. Then we saw denoising autoencoder where we add noise and then try to uh, generate the original XI. And this adding noise, yeah, acts like a regularization because the model has to learn a robust representation. And then after that, I think we looked at sparse autoencoder, where we want the activations in the hidden layer to be sparse. So we add an additional term to the loss function to get that desired behavior. Okay. So we fix this parameter tau, okay, to the sparsity that we want in the network. So this would be a hyperparameter, and then to achieve this, there is another term, this one. Okay. This is just computing cross entropy between the desired and the target sparsity. So this also acts like regularization. Okay, and then after that, in the contractive autoencoders, okay, so we put a condition on the Jacobian. We want it to be smaller. Uh, So this means Jacobian is just gradient. So we are enforcing that the network is like uh, the hidden representation should not be very sensitive to the output. Okay. So what happens eventually is the network only learns important, very important features of X in the hidden representation, hidden latent representation. And so I think that was it for this week. Okay. So any questions or doubts regarding, so any doubts you have about whatever was covered this week? Fine, moving on. So I have these three regularization term. Okay. So which we saw in the lecture. So could you like tell me which one is for what type of autoencoder? So what are we doing with the first one, the second one, and the third one?
So for the first, we have L2 regularization.
Yeah. So what happens in the L2 regularization? So what are we trying to enforce?
So we are trying to enforce that the weights are within a certain limit. We don't want to cross the limits.
So here, okay, we are just taking the L2 norm. So we want the weights close to be, it should be close to zero. So that is what we are encoding. So we are constraining the search space, and yeah, that helps in regularizing the model. Okay. So what about the second? What is happening here?
This is basically binary cross entropy.
Yeah, binary cross entropy.
No, but
So
if I'm not wrong, cross entropy also have a negative sign, minus y into log y cap. I don't see that over here.
so this is cross entropy, right, between two distributions. So
Yes.
when you take this outside, you'll get the negative part. So rho log rho minus rho log this rho cap.
Oh yeah. Basically, the rho cap is the denominator, so
Uh,
negative. Yeah, yeah, that makes sense. Yeah.
so yeah, where did we say this regularization term?
Basically, in classification task, you can find this
Now, so for
after applying
autoencoders, the different,
softmax.
yeah, yeah. But here we saw now the different types of autoencoders. So, so in the context of this lecture, where was this used, the loss function?
When you have inputs are basically binary, then you use this.
Yeah, yeah. But so this was used in sparse autoencoders. Yeah. So this is the exact regularization term that was used, and this rho is the sparsity that we want to induce. So is this not clear? So do you want me to go over this? And what about the last one? Where was the last regularization term? This is Frobenius norm of Jacobian, no? So this is the regulation term used in the contractive autoencoders. Okay, so let me go over this, what is basically happening here. Okay, let me open the HS mode. Okay. So what normally happens is you have input, you pass it through the network, and you get y dash. So one loss is between this xi and xi hat. Okay, so what you could use here is the normal MAC loss. You want the output of the network close to the input. So that is what autoencoders do. Okay. But in addition to that, what we want is the hidden activations that we get in this hidden layer H. For example, there are one, two, three, four, five, six activations here. So we want these individual activations also to be very, very small. Okay, very close to zero. Okay, so basically what is happening in sparse autoencoder is we are computing this row hat. Okay. So the activation over here that we're using is sigmoid. So basically we'll get a number between 0 and 1. We can uh, see them as probability values. And we are computing this average. So in this case, there were 5 values, which are output of the sigmoid function. 6 values will average all the 6 values and get this row. And this will tell us the sparsity. I can hear noise. Can you switch off your microphone? Who's that? Yeah. So this is the row hat that we saw for layer L in the slide. Okay, so this tells us the sparsity, and we want to control this sparsity metric. So for that, what we do is we fix we can see this as a distribution, right? Okay, and yeah, so you can think of this as a binary distribution. So when x equal to 1, uh, with x equal to 1, this has the probability of rho hat. So similarly, there is this target distribution that we set. So it's a hyperparameter. And we want to induce this sparsity. So for that, we add this binary cross entropy term. So we want these two distributions to be equal. So yeah, in addition to the reconstruction loss, we have this sparsity term as well. And similarly in the contrastive, so these are different regularization techniques that people have found to be useful. Okay, so similarly there is one involving Jacobians. So this one. So that was the final equation related to contractive autoencoders. So so there are two factors here. Okay, two opposing factors. One, you're saying in the actual loss function where you're taking MSE, you want H to be very sensitive to the output. Okay, okay. But here there is opposing term that you don't want the hidden layer, the hidden activations to be sensitive to the output values. So these two opposing somehow regularize the model, and it reduces the search space of the model and inducing biases of how the weight should be. Okay. Yeah. So the last equation was from the contractive autoencoder. Fine. So moving on, we'll solve few questions now. I've taken this question directly from like previous year questions of previous year assignment of the same course. Okay. So I'll read out the question and yeah, we'll collectively come with the answer. And suppose we build a neural network for a 5-class classification task. Suppose for a single training example, the true label is 01001, while the predictions by the neural network are 0.25, 0.3, zero point 0.2, zero point 0.1, and zero point 0.2. What would be the value of cross entropy loss for this example? Yeah. So answer up to 2 decimal places and use base 2 for log calculation. Okay, so one correction. So this is actually not cross entropy. So this is actually KL divergence that we are computing here between two distributions. Okay, cross entropy is just P log Q hat. So yeah, so basically you have to compute cross entropy between these two distributions. Okay, so it's negative P log Q. So you have to compute this for all the values. So because there are just two terms active, so finally we'll have to compute log of two values and add them up. So has anyone computed this value? Like, should I go ahead and tell the answer, or is anyone computing? Yeah, so the answer is this 4.05. Okay. I've just taken log of zero point 0.3 and zero point 0.2 negative that. Moving on. So any questions? It's just there's a formula, you just have to plug in the values and get the answer. So yeah, let's move on. So if an under complete autoencoder has input layer with dimension of 7, what could be possible dimension of the hidden layer? So under complete means the size of the hidden dimension is less than the input. So what would be the answer to this question? Yeah, anyone? So A and D. Yeah, C is 0. 0 would make sense. So it should be 6 and 2. Yeah, so it's 6 and 2. Suppose for one data point we have feature x1 to x5 as this. Okay, which of the following function we use on the output layer, the decoder? So we have these values, floating point values, and we want to, because we are using autoencoder, we want to generate this value. So what would be the uh, function that we have to use? The decoder. and Neeraj as ReLU. Now it's just linear layer. The answer is linear.
Why specifically linear? But
Okay, so yeah, so only one option is correct, right? So we have to choose one which is like which will get good results. So if you see ReLU will cut off the negative values. Okay, and we won't be able to. There is -3 as well in the input, right? Okay, so if we use ReLU, we won't get this negative value as output. So we want to cover
okay,
all
makes
the.
sense.
So which of the following statement about regularization in autoencoder is always true? Regularization reduces the search space of weights for the network. Regularization helps to reduce the overfitting in overcomplete autoencoder. Regularization shrinks the size of weight vector learned. All of these. D. Okay. So the first one is correct. It reduces the search space of the weight for the network. And the second one is also correct because yeah, it helps overfitting. Now regulation shrinks the size of the weight vectors learned. I don't think this is correct. It does not always like shrink the size. So it should be A and B.
By size, do we mean the dimension over here of the vector?
Okay, so that is also not clear. So
Or by size, do we mean the L2 norm of the vector?
L2 now, yeah. So that is not clear. Hmm. So yeah, so what happens in L2 norm is yeah, you want the weights to be close to zero. So this is a bit ambiguous, but you get what is trying to ask. Right, yeah. Okay, fine. So yeah, let's move on to the next question. So the first two are correct. This third one is a bit ambiguous. So if the third one is also correct, so in L2 norm, yeah, weights are close to zero. We can call that shrinking of the size. If it's talking about L2 norm, then this is correct. But yeah. So what is the purpose of a decoder in an autoencoder? To reconstruct the input, to generate new data, to compress the input, to extract features from the input data. Yeah, it is correct. To reconstruct the input data. And moving on. What are the advantages of using a denoising autoencoder? Robustness to noisy input data, reduction of risk of overfitting, faster training. It promotes sparsity in the hidden layer. Okay, Q6A. Yeah, so the first one is correct. The second one is also correct. Reduction of risk of overfitting. The third one is incorrect. And yeah, there's nothing sparsity. There's no explicit sparsity in denoising. So yeah, so it should be A and B. Oh no.
So can we say that this is also a regularization technique?
Yeah. So this is also a regularization technique. Yeah. Yeah, so when you add noise, yeah, this is also a regularization. So there are various other ways as well. So dropout is also, if you have heard of dropout, where you randomly drop some of the activations from the network. Okay. So that also helps in like reducing the risk of overfitting. So this is also, yeah, you can say that this is a regularization technique. Okay, moving on. So we are given an autoencoder A. The average activation value of neuron in this network is 0.06. The given autoencoder is contractive autoencoder, over complete neural network, sparse autoencoder, denoising autoencoder. Yeah, the C is correct. So which of the following problems prevent us from using autoencoder for the task of image compression? Images are not allowed as input to autoencoders. Difficulty in training deep neural networks, loss of image quality due to compression. Autoencoders are not capable of producing image output. Yeah, so this also, the first one is wrong. Second is also wrong. And the last option is also wrong. So yeah, third one is correct. Mm. So which of the following is a potential advantage of using an overcomplete autoencoder? Reduction of risk of overfitting, ability to learn more complex and nonlinear representation, faster training to compress the input data. So overcomplete means the dimension, so number of activations in the hidden representation is more than the input. So what should be the correct answer to this question? So what do you think about the first option? Re- Reduction of risk of overfitting. Is this true?
I guess it depends. If you have certain regularization, then you can say yes, but not
Okay.
generally.
So yeah, but there is a risk, right? So what could happen, like if the size of the input is very large, what is one way the model could overfit? It will just memorize what is happening and will not generalize. So how could that happen? So could you like tell me one case, which I think which was discussed in the class as well. So when the hidden dimension is very large, what would happen is the model could directly copy the input uh, in the hidden dimension. So it's not learning anything. So there is high risk of overfitting. So that's why we have to come with some regularization term for it to learn things. So what was the second part? Ability to learn more complex and nonlinear representation. Yeah. So what are your thoughts on the second option?
I would probably say this is the odd one out, but I don't know the logic. Why is it so?
Okay. So what is happening is, so suppose the input dimension is D, and from that you're moving to a higher dimension, say D prime. Okay. So when you're moving from a lower dimension to higher dimension, okay, so you have like a lot of space where you can suppose something is not linearly separable in the lower dimension. You can move it to a higher dimension, and it'll be easier to move those data points in the higher space. Uh, so yeah, it's it becomes easy to separate data points in the higher dimension. So is that intuition clear? You can think of it as you have suppose your points are in 2D plane. So it's the same point. Suppose there are 4 points. Okay, so in 4D, in the 3D space, you have a lot of space in which you can move these 4 points. So you have added a degree of freedom. So it becomes easier to move the points around and come up with like the decision boundary if you're learning a classifier. So learning becomes easier and you can learn this complex relationship.
Okay. Maybe you can show in the coding exercise. That would be helpful, I guess, if time permits.
Okay, okay, fine. Let's see, I'll think about like how to explain this. Yeah. So this is in general for all neural networks. So basically you increase the dimension so that, so even if you're training a neural network, normal neural network, so what you do is you, in the middle layers, you try to bump up the dimension, number of features of the network so that the points move to higher dimension and there it's easier to uh, separate out the points. Okay, so let's see. So in the next lecture, I'll have a demonstration for this. We'll have to see how to do that. But yeah, the second one is correct. The third one is incorrect. The last one is also incorrect. Okay. So which of the following is a potential disadvantage of using autoencoder for dimensionality reduction over PCA? Autoencoders are computationally expensive and may more require more training data than PCA. Autoencoders are bad at capturing complex relationship in data. Autoencoders may overfit the training data and generalize poorly to new data, and autoencoders are unable to handle linear relationship between data. Okay, so let's look at the first option. Yeah, so PCA you can get the values in one shot because there's a closed form solution. But here, yeah, you'll require more data and you'll have to train this network from scratch. So yeah, so autoencoders are a bit expensive computationally. So the first one is correct. Auto encoders are bad at capturing complex relationship. They can capture complex relationship. So this is also because we are using uh, yeah, matrix multiplication followed by a non-linearity. So that's why it can capture non-linear relationships as well. Yeah, yeah, it can overfit and generalize bully. So this is also a disadvantage. Okay, so we'll need to add regularization term and tune the hyperparameter, the contribution of the regularization term in the mean loss function so that the model doesn't overfit. Okay. And the final answer is also incorrect because we saw a link between PC and autoencoders. And we saw if we use linear layer, the autoencoder just comes up with the hidden representation, the latent representation that we get with PCA. So this is also incorrect. So it's A and C. Any doubts regarding this question that we saw? Okay. So now let's move on to coding and let's complete. Let's see what we saw in the previous lecture, previous session, and we had left. Yeah, we were not able to complete this topic modeling. So we'll go through this again and see. Yeah, complete this. Okay, so we saw how. Okay, so let me like recap what we did. So we saw how we could do background removal with PCA. Okay, so the goal is so there are people moving here. So we want to remove these people from this image. So you want to separate this out into background and foreground to these two components. So the way we did that was so this is a video. So our input was this video. Okay, and we want to remove people moving over here and just keep the background. So yeah, so we did that by applying PCA. So way we did was we first converted this. So an image is made up of frames. So video is made up of images. So we took those individual images and uh, converted the uh, 2D matrix of the image into a single vector. We stacked all such frames together. Okay. And yeah, so this is an image taken from the sample from this video. So we took that, we converted this into a vector by just resizing this matrix. Okay. And we stacked all such matrices together. Okay. So this is what we end up with after stacking all the frames from the video. So here the x axis denotes time. So for different time step, we have this, and y axis is like uh, flattening out this image into one single vector. Okay. So what we observe over here is almost everything is uniform, but you see these lines in the middle. Okay. So all these lines are because of the people moving in the video. That is causing this line. Because the only change between the frames are these people. The background remains constant. So when we convert this into a vector, the patches that we get are because of the movement of the people. So changes, so as the x-axis denotes the time, the changes between the two images are because of the people moving. So this is what we get. So we took this image and directly used sklearn and uh, yeah, used a randomized SVD call, came up with this UV and X, and we just took the top two singular values. Okay, so we have this, and yeah, so we have removed everything and just kept the top two singular values. Okay, so this is what we end up with. So these are the dimensions, and yeah, so using this, we'll again reconstruct this big matrix again using only the top two singular values. Okay, so that is what is called a low rank approximation of this matrix. So this is big. This is a big matrix with all the information. We do that decomposition, get U S V, and just keep the top singular values. We are just considering the important features which are present in the image, and the important are basically uh, the background and the foreground goes away in that low rank approximation. Okay, so yeah, so we reconstruct this again after SVD and removal of the singular, just keeping the top one singular value. And then, yeah, so we see that those patches are not present over here in this. So we have removed the all the people that were present. And yeah, so this image is, we take a column from this, okay, which is an image from a timestamp from that video. And when we plot that, we'll see people have been removed from this. And when we take the original image and subtract this low rank approximation, we'll see we'll get the foreground as well. So yeah, so SVD can be used in this manner, yeah, to separate out the foreground from. So this is an application of PCA. Okay, so this is what we saw in the previous one. Then we saw instead of using two, what if we use just one singular value? And with that also we get a very good result. Okay. So after that we saw a robust PCA. Okay, so there instead of getting this low rank approximation, okay, so what we are doing is we are just sub like we are trying to decompose this matrix M into two parts, L and S. So this is the optimization that we are doing here, where L is the low rank part and S is the sparse part. So yeah. So this is the objective function. This is the nuclear norm. Okay, to get the low rank approximation, and this is the explicit sparsity term that we're having. So whatever noise is present, we'll get that in S. Okay, so foreground will be present in the X vector, and L will get us the low rank approximation. So here, we just came up with the low rank approximation, and whatever was left uh, was was considered as the foreground. But here we are explicitly modeling the two components. So yeah, so this should give like better results than this. We didn't go through the algorithm in detail. We just so I have shared the code. You can go if you want. There's a paper also uh, explaining this. Hello? Yeah, I think I was dropped from the call.
Yes, I
Okay, some.
guess
Okay. So till what portion were you able to uh, hear me?
you were showing us the helper functions of the robust PCA.
Okay, okay. Okay, so send us code to explore this concept. So I've already shared all the code. The code is I'll be covering in this related to autoencoders that also I've shared. So if you have access to the drive, you can like follow along and like run all the cells along with me. Yeah. Okay, so yeah. Okay, so robust PCA, fine. Yeah, so we were explicitly modeling these two components, LNS. So with this, we get like better results compared to the normal PCA. Okay, moving on. So the next thing that we saw, we weren't able to complete this properly. So we'll continue with this. So it won't take much time. Okay. Basically, what we are doing here is we are given a corpus. So there's a corpus and there are lots of documents present, and we want to get an idea of what topics are present in all those documents. Okay. So for that, what we'll do is we'll first construct this term document matrix from the corpus. So given a document, this records what words that were present in that document. Okay, and this number is the frequency of the word in that particular document. So we'll first come up with this matrix, okay, and then directly perform SVD on this to get an idea of what topics are present. Okay, so what happens in PCA is you will get like the eigenvectors. So eigenvector captures like uh, most of the variation in the data. Okay, so what we expect after this is given like this M, this huge matrix M. So M is number of documents in our case, and N is number of words. We'll approximate this with a smaller. So we'll come with this SVD and only consider say top R values and drop all the rest of the values. Okay, so what we say in this, the R vectors that we get, okay, which are so that will say ki those are the topics. So the important features that we get out of this decomposition, those represents topics which are present. Okay, but we don't know what these topics are. So these are some higher dimension representation that we're getting. To get a sense of what these topics represent, what we are going to do is we'll look at the words which are present for that particular. So to get an idea of, suppose, say the first topic. So the first column would represent some topic. So to get an idea of what this topic represents, we'll look at the second V transpose matrix and look at the words which are like which contribute like highly to this particular topic and get a sense of this. Okay, so yeah, so this is like an application to model which are all the topics which are present in the documents in this corpus. Okay, so this is one way using SVD, and the other way which we saw is this explicitly breaking down this into two. So this is called non-negative matrix factorization. Okay, so directly given a matrix V, will decompose it into H and W instead of these three matrices. Will directly use this break down into two, and the first one is topics, and yeah, so there's no singular value over here. So we'll use SCD and then directly model this. Okay, so yeah, so is this clear? Okay. So for this example, yeah,
How
we
do
took
you how do you decompose matrix V into W and H?
uh okay, so what we do here, what we'll be doing here is uh we'll initialize W and H, okay, randomly, like how we initialize a neural network. Okay, and then we'll define a loss function that W into H should be equal to this using MSE loss. Okay, and then yeah, so we'll perform SGD and yeah, come up with this W and H directly. So instead of yeah, what we did here was we applied some maths and then came up with this some optimization function, and then we did this optimization and then we came up with this eigenvalues. So the way to decompose this is you take A transpose A and then find the eigenvalues and get the values. So instead of taking that route, what we'll do here is we just want to break this into topics, right? So yeah, so what we normally do in neural networks, instead of using any non-linearity and all, yeah, we'll do the same thing, but yeah, we'll just initialize this randomly and then yeah, we'll define a loss function, and yeah, so in the optimization process we'll come up with this WNH. Okay, fine. So the data set that we so this is the data set, news group data set. Okay, and we'll just so I think there are around 20 topics in it. We'll just look at these four topics. Okay. So there are 2K training points in this data set, and here are some documents that are present over there. Okay, so we have just used these four topics, and we'll later see after topic modeling we should be able to recover these topics when we look at the words which are active for this topic that we are modeling. So this information about the topic, which is the ground truth, we are nowhere using it. Okay, so basically this is unsupervised learning that we are doing, but we'll see breaking down into these matrices. Yeah, it'll try to model topics. Okay, so the first one is related to graphics. Okay, second one I guess is related to religion, and third one is space.
Can you explain the task once again? I'm a bit confused. Like, what are we planning? Is it more of clustering task we are performing via SGT?
Okay, uh, basically, yeah, the task is you want to find what topics are present in the document in this corpus.
Okay.
Okay, so I am saying ki if you just do this matrix factorization, okay, so what you'll end up getting are the topics in the important components.
So
So
in the
base,
data matrix, each row represent the particular column or the paragraph we have, right?
yeah. So each row is a document over here.
Right. Mhm.
Okay, so you can uh, yeah, so the row is number of documents and column are the total number of words which are present. So so
Right.
your yeah, so word so the words which are present, you can think of these words give an idea of what topics are like, about the topic of the document. Okay,
Okay, so
so
we
your
have frequency of certain words. We are not
yeah.
taking frequency of all the words, but certain words itself, right?
Now, so over here, so given a document, it'll have, so I'm considering all the words right now. Okay.
Okay, right.
So so first what will I do? So if I go to implement this, what I'll do is I'll pass through all the documents. Okay, see what all unique words are present in the entire corpus. Okay, so and I'll fix a vocabulary. So that'll be vocabulary for this particular corpus, which consists of a lot of documents. Okay, so once I have the vocabulary I'll do another pass. I'll go through each document. I'll see. Uh, so in that document, what word was present, and then I'll record that frequency of that particular word for that given document. So
Right.
after that, I'll end up with this document term matrix. So I'm recording the frequency as well as the term present. So if a particular word was not present in that document, so it's that entry would be 0.
Right.
Okay, and these words tell us like what is the topic of the document. Okay, but since there are a lot of words, it won't be like explicit key what. So what we are doing is instead of that, we are decomposing this big matrix M cross N into M R, considering only the top say 6 or 8 singular values. Okay, so in that higher dimension, we'll assume that so you can think of these vector as some combination of the words. Okay, that we are getting when we decompose it in this manner.
Right.
So some sort of implicit clustering is happening. Okay, because yeah, so
Is this
we
is this something similar to word embedding?
uh so you can think of it as word embedding. So initially, yeah, people uh, used to do this topic modeling and use this for initializing the word embedding. Yeah. So somewhat related to word embedding. Not exactly, but yeah. So the information that we get from here also could be used to initialize the word embedding when you're training the neural network, because this gives some information, right?
Mm.
So, so what is it clear what we are exactly doing? See, so the information about the topic is present in the words. So, but it's not explicit because there are a lot of words over here. So instead, what we are doing is we are baking this matrix into this and only considering top 8 singular values. Okay, so this uh, now the singular values will like represent some topic which would be like combination of words. Okay, and to get idea of what topics are represented, when we'll look at this V transpose matrix and see uh, for what entries for that particular topic will get like words which have higher weightage in that.
Mm. Right.
This is one way of doing this, and this is the same task that we are doing. Instead of using this matrix decomposition, we are uh, defining the matrices like this and learning it from scratch. What normally happens when you're training a neural network. There is no non-linearity, just two matrices. Okay, so this is the data set that we are considering. Okay, and we already know the ground truth, but we'll nowhere use this when we come with the topic. Okay, and here are some of the documents which are present over in this. Okay, these are the topics. So we want to tokenize all this and then form this document metric. So there is a function in sklearn called count vectorizer. Okay, so that gives us this matrix. So we just have to give a list of documents like this. It will form a matrix and give it to us. So we have a matrix. Okay, so there are 2K documents 2034 documents present, and this is the number of unique words which are present. So this will be our vocabulary size. This is how you can, so this is the matrix that we get. You can also, by doing this get features out, name out, you can get the actually text corresponding to each of the column. And yeah, here are some of the terms present in the words present in the corpus. So to model the topic, we'll just take this matrix, these vectors, and perform decomposition on it.
So which documents you have used?
So I've used documents from this news group dataset. Okay.
Okay.
So it's a so basically people post about so these are posts of people in that website. It's a collection of that. So this is complete. Okay. And this is what we get after single value decomposition. Okay, so the U matrix that we get after decomposition, those vectors are orthonormal. So it's a orthonormal matrix. Guys, to just to verify that I've done this. Okay, I'm just taking U transpose U's, and this should be equal to the identity matrix. Just to verify that I've done this. This should output true. And now what I'm doing is I'm just looking at the singular values, okay, which we get here. And we'll just consider top 8 singular values and see what topics are modeled. So this is what we get as output. Okay. So we're looking at top 10 topics model, and you can see the second one is related to graphics. Okay. This one is related to religion, but there is graphics in it also. It's a combination, but yeah, mostly. Okay, so this is again about God, atheism. This one is about space. Okay, so we are able to like recover the topics. So looking at the word, we can see what this documents are about. So we just chose four topics. Okay, nowhere use this. Okay, but yeah, we will able to recover by doing this decomposition. So is this clear exactly what we are doing here?
How do you evaluate this? And like any metric, like
It's
okay, we have four categories right now, we have eight.
mhm.
So among the eight also could we further sort of classify them to get a better understanding, like there are only four categories.
Okay. So here what we have done is yeah. So there might be some metric, but here we are just visually observing. It's able to retrieve the topics that we started with. Yeah. There could be metrics, like I have no idea.
What
I
if you only take top four values? Like what would be the output look like? Can you check? Like the
Stop.
number of top words, take it to 4.
Okay, so that would be the four top four now.
Yeah,
These four. So these are the
right.
top four. Yeah,
But that
top four
won't,
topics.
yeah, that won't capture the whole classes, right? Because,
Yeah,
yeah.
yeah. So there's about there's something about graphics over here. The second one is also graphic.
I'm like, second one is very conclusive. It is related to graphics. Third is a bit ambiguous because it has edu, pub, mail.
Yeah, oh, yeah, yeah.
Third is clear, sort of related to,
To religion, yeah. But there is
yeah.
also about graphics, yeah. But
Mhm.
yeah, it doesn't cover the space part.
Yeah.
So we are not guaranteed to get all the documents because we are not using it anywhere. We're just
Mhm.
basically starting in, yeah. So this is just to get an idea roughly of what is happening when you do this SPD.
Mm.
Okay. So yeah, you could recover topics. You're not guaranteed you'll get everything, but yeah, somewhat when you so basically it is trying to capture like the important directions, right? Where the variance in the feature is very high. So when you do that, there's some intuition ki you'll get the important topics. You're not guaranteed to get, but you observe that you get all the topics, right? Yeah, so if we dig deep, I think you'll find ways to validate this as well, but I'm not aware of it. Okay.
Even
Yeah.
like the vocabulary size itself would be sort of like a hyperparameter in this case, right?
Uh, so now we are considering all the, so it's not a hyperparameter, right? So hyperparameter, it's not hyperparameter. We are considering everything which is present.
Oh, okay.
Yeah, so we consider all the words in the document and come with this matrix, and then doing this decomposition to recover the topics.
No, but like you are saying that 26,000 words, consider the all the words possible in English. Is that what you're saying?
It's not all the words possible in English. So whatever words which were present in the doc corpus,
Okay, you're taking the unique words and then you're
unique words,
creating the
yeah, creating
vocabulary
this
side. Oh,
vocabulary.
oh, okay. From the document itself, you're meaning.
Yeah,
So
yeah.
this is dynamic then, right? This would
Hmm?
change if you take. This is
So yeah,
dynamic, the
yeah,
vocabulary.
yeah. So if you take some other corpus, it will change.
Right, right. Okay, got it.
So what is
So
this graph?
so these are singular values that we obtained. So so if you look at this after decomposition, the S that you get. Okay, so I've plotted this to get a feel of how the values change. So if you look at this, you'll get this. So here I'm plotting all the 20K singular values. So if you, it starts with 400, around 400, it drops drastically. Okay, so there are very few important features.
So what is on x and y axis?
So on x-axis is different singular values. The first singular value, second singular value. Okay, so it's the position value, and the y-axis is actually actual singular value that we get after the decomposition. So this S, I'm just plotting this S matrix that we get out. So when we decompose it, right? So this matrix sigma is just a diagonal matrix. Okay, with the values in the diagonal sorted according to from highest to lowest singular values. I'm just plotting this.
Okay.
So so this plot, like the way it decreases, gives an idea ki how like uh, so there are so if we consider this as a vector, document as a vector, okay, so it could be that these and this n as features of the document. so there could be like lot of correlations which could be present in these features. And basically, instead of considering this very high dimension, it could be that this data points are basically could lie in some lower dimension of that higher dimensional space. Okay, so yeah. So when it drops drastically like this, okay, so there are a lot of correlations which are present, and considering all these features are not necessary. Okay. So suppose you are doing some classification task, instead of doing this, you can do this SVD and just take top R values, and the U matrix that you get, you could use that as so that is what we do in PC, right? Dimensionality reduction. Okay. Reduce the dimension and use that instead of using the full matrix. Yeah. So what we did over here using SPD, we'll do the same thing. Okay. But yeah, we'll use gradient descent over here. So again, instead of using the count, I'm computing the TF-IDF vectors here. Okay, so I get this sparse matrix. Okay, which is again this. So so what happens is, instead of taking the raw counts as input, I'm taking the frequency of the word. Okay, and then normalizing it by number of times a particular word appears in different documents. So suppose there is a word which is common to all the documents, that means that word is not that important. So I'm penalizing words, those words which are like present in most of the documents. So yeah, I'm computing this, okay, and I just want the size of W to be M into D. So yeah, so I just want to model 8 topics over here. So I initialize this tensor, okay. So this is our target M. Okay, and I'll randomly initialize these two WNH metrics, and I want the entries of WNH to be positive. Okay, so that's why I'm taking this absolute value. Okay, so this is the shape that we get. Okay, so I have defined a loss function here. This is just MSE loss. I'll be using Adam optimizer that we saw last to last class. I've chosen learning rate as 0.05, and these are the beta parameters. Okay. Fine. So in addition to this, I'll add two more terms, like I'll add a penalty. I want this WNH to be positive because I uh, suppose, so I'm looking at the contribution of a particular word based on H, right? So H is this matrix that we have. Okay, so for a given topic, what all words are important? For that, I'm looking at the highest entries which are present over here. So if it is negative, then it doesn't make sense, right? What is our negative contribution of a word towards a topic? So for that, I'll enforce one more penalty so that I get all the entries as positive. Okay. So this penalty is on WNH, and uh, lam is like lambda will be a hyperparameter. So I'll initialize lam to be very high, 1.6. So I don't want WNS to be negative. So what could be a possible loss function for that? Uh, so what I could do is I could take, suppose there is a negative entry. So I'll clamp, so I'll find out what entries are negative in H. Okay. So this will return all the negative entries which are present. So let us take an example and see. Suppose I define a tensor -1. So this tossed and clamp with maximum this will return all the non-negative entries which are present. Okay, so I don't want non-negative entries in my matrix. So what I'll do is yeah, I just take this and square this so that I get positive value. Okay, so this will be my loss function to penalize if the entries are negative. Okay, so I want to do this on both W and H. So let me define another function neg penalty. So I'll take a matrix X, do this operation, and return the value. So I have to do this on both the matrix H and yeah. So what it returns is a matrix. So I need a number. So I'll just take the mean of this. Similarly with W, this is just extra term that I'm adding to the loss function so that I don't get negative values as output. Yeah. Now let me go ahead and train this network. So after this, like I'll get a matrix. So here we applied like mathematical concept and came with eigenvalues, did this optimization, got this solution in like closed form. But here we use another approach that we normally use these days. So we want this factorization, right? So we just randomly initialize. We picked up a loss function and then yeah, use SGD to finally come with this factorization. And we'll use same the function which we used here to see what topics are present. Okay, sorry. So any questions? What is happening here? Is everyone able to understand what is happening here? So it's same thing that you're just doing SPD, but yeah, but using SGD to come with that factorization. So let this finish and we'll see what topics are more. We'll do similar analysis that we did over here.
The negative values could also signify, like, let's say, happy and sad, right? If in your
Mm-hmm.
word vocabulary you both have happy and sad, and if you're, let's say, classifying a document, you're doing
Mm-hmm.
sentimental analysis. So if you have, let's say, document plus 0.23 for happy and minus 5 for sad.
Uh,
So you can say that the document is tending towards more happy since sad is negative over here. So can you, I don't know if you can think along this line or not.
yeah, but it'll be easier to model, right? If the all the uh, all the contributions are positive. So in your case, if it's instead of negative, it's zero, and the corresponding value. Uh, so you took happy and sad, right?
Yeah.
So you said sad is negative and happy is positive.
Mm.
So instead of that, the sad part could be zero and could be more positive value. So after that, what we could do is we could normalize that vector and like get all the contributions and see easily which one is contributing and get a better idea. So you're also correct. That also could be one way of interpreting. So yeah. So I want it to be positive. So I enforce that in the loss function.
Okay.
So yeah, so this will also like tell you how to bias. So when you're training a network, so you can add biases of what you want, what particular behavior that you want from the optimization technique. Okay. I think basically this thing was done for eigenfaces. They wanted so what happens in eigenfaces so what we did in SPD could get so you find out which features of the faces are important and take like those and see which contribution of those features of face you get the final face value. So there's a paper called Eigenfaces in which they use negative matrix factorization because there a negative contribution for a given feature they were not able to uh, so their negative value didn't make much sense. You have a feature of face that is negative, uh, it is not that interpretable. So if all the values are like positive, it's easier to interpret. So here the sad had a meaning to it. So you could like the negative of that could be like positive. Negative of sad is positive. Something like that could be considered.
Yeah.
But yeah, so when you have just faces where things are not that interpretable, so I don't know. Yeah, there this could help. So are you getting what I'm saying?
Yep. I guess when you, like, the training would be much faster if you don't consider the negative values
Mhm, yeah,
also, right?
yeah, yeah. There is some error over here. Let's see. So I'm what I'm doing here is I'm going through each row of A and then passing it through this, and it's just retrieving the upk documents and joining. Step size must be greater than zero. Let's see. Okay, so I have the documents. Okay, let's take this out. Why is it throwing? Okay, because it's a tensor. Fine. So because it was a tensor over there, we're not able to use a negative step size, but after converting to numpy array. So again, here also we can see this is related to religion. It's talking about Jesus, I believe. This here, okay. Other than this, these terms are about graphics. Okay, so this is about space. Okay. This is again about space. This university as well. I don't know how that came in, but yeah, after that again religion. So you can see you are able to again recover the topics. Okay. Yeah. So any questions related to this? So after this, we'll move on to uh, autoencoders. So we'll look at variational autoencoder. We'll take a. It was not covered in the class, but yeah, we'll do that and we'll see. We'll just then we'll take the decoder which is learned and then start with a random noise and try to generate the image again. So any questions till now? Okay. Yeah. So we'll use MNIST data set over here. Okay, so we'll pass the image to the autoencoder, get the output, and put the reconstruction loss in. Okay, so here is the data set where I'll be saving the data. Okay, so I'll be using this torch vision library. Okay, so there we can specify what transforms that you want. So I'm saying here ki I want tensor as output. Okay, and then these are other parameters like number of workers to use and all. Also in the training process, I'll like uh, fix this batch size to 100 in the optimization process. Okay, so these are some of the parameters. Okay, so I'll use them. So this function, when I call it, will download the data set. Okay, and give me this data set object. Okay, and then after that, using that data set, I've constructed this data loader as well. We'll see what data loader is and what data set is. So basically, it's a wrapper. So if you look at the object, okay, so when you index into a data set, it'll return like one image. Okay, so let's see how many images are there. So when you do this length, so there are 60K images present in this data set. Okay, similarly in the test data set, if you look at the length, okay, let's first test and train. So in the train there are 60K data points, and the test there are 10K. Okay, so let's go ahead and plot an image. So we saw when we index into this, it'll return, okay, two things, the image as well as its class. So in the first one, we have the image, and the second part of the tuple is the class of the image. So this image is of number 5. Okay, so where I'm plotting that using matplotlib. Okay, so okay, so that was about data set. Okay, so what data loader gives us it, instead of giving just one image, so when we iterate over this object, we'll get a bunch of images. Okay, so this is what the neural network will see. Okay, so during each step of the optimization, okay, we want to form we need a batch of images, right? So that will be returned by this data loader. Once we have this batch, we'll use that. We'll do a forward pass through the model. Okay, then compute the gradients and update the parameters based on that. So this is what will return us the batch of images. And we have told it ki during training, so for the training data loader, we want so we have specified the batch size, and we want the data to be shuffled. So it will randomly shuffle the data and then give us batches. And after each epoch, that means once it has gone through all the images, one, it will again reshuffle it and then again give us the batches. Okay, so let us look at this DL class. So it's a the class of this variable is data. It's from our data loader class. Okay, so if you want to get a batch, okay, so what we'll have to do is we'll have to convert it into an iterable and call this next function. So this will return like a batch. So we look at the batch. Okay, so the first one is the X value. We look at its shape. So we have 100. So because we have specified batch size as 100, so we'll get 100 images. And this is the size of image, 1 cross. It's a grayscale image. So number of channels is 1, and there are 24. This is the height and width of the image. Okay. And similarly, if you look at y, over here we have all the uh, ground truth value, the labels for this patch. Okay, so when we are training this auto encoder, we don't need that y part. We'll just use the x part and try to reconstruct it. Yeah. So this is the encoder. Okay, so in the lecture we saw that there was just uh, one matrix operation, right? One matrix operation followed by a nonlinearity, and we'll end up getting the latent features. This is the hidden network. So, but here, so there are two differences here. So one is I have two. So there's a we have two layers over here, and instead of predicting the latent representation, okay, what I'm doing here, what happens in variational autoencoder is you try to predict the mean and the variance of the distribution in the latent space. Okay. So basically you want to find you're trying to model P of X, right? The distribution of the data points. So we'll do that directly. So give an image, and we'll we'll assume it comes from a Gaussian distribution, and yeah, the latent comes, and we'll directly try to model this mean and variance of the hidden representation. And this is the activation function that we are using. So it's a Riki ReLU. Okay. Let's see how Riki ReLU looks like. Okay. So in normal ReLU, values less than for negative value, will threshold all those values, right? But here you have like a slight slope. So advantage is so gradient will pass even though in this region as well. So will not, so training would be faster because yeah, there'll be higher flow of gradients. So in ReLU, when the values are negative, gradient doesn't pass back in the backward propagation. So here the gradient will flow and training would be faster. Okay. Yeah. So the difference over here from the lecture is that we'll predict this mean and variance of the distribution. Okay. So forward pass would be given an x. Okay, you will pass through the linear layer, pass it through the activation function. Okay, so this is the hidden representation one, and similarly we'll again pass it through the same pass it to the second linear layer, apply the activation, get the hidden representation two. Okay, and then use this hidden representation to predict the mean and the variance. Okay, of the latent distribution. So this is our encoder. And then the decoder uses this and again reconstructs. If you see the dimension from input, going to hidden dimension, and then finally this is the latent dimension that we have. Okay, and from over here we'll move from latent to the final output distribution. Okay, so this is our decoder. Okay, so we'll have to combine this decoder and encoder and decoder and come with a full model. So this is, I've defined another class for that. Okay, so we have the encoder as well as the decoder. Okay, so we'll encode, get the mean and the variance. We'll apply this reparameterization trick. Okay, so, where we use that mean and come up with this latent representation Z and use that to finally uh, come up with the output. So we'll pass this Z. So this is a reparameterization trick that is used in variational inference. Okay, so I'll not go into details of what that is, but yeah, if you want me to go, I can like have a lecture on that variational autoencoders and go through maths of deriving how this maths behind all this, where we instead of coming with this Laplace, you model this mean and variance. Okay, and then when you want to generate an image, you'll sample from this distribution and then pass it through the decoder. This is the model that we have. Okay, so here I'm defining the xdim, the dimension of the input, so which is just 28 cross 28, because we'll convert this into a vector and then pass it through the model. Okay, so I have defined the model over here. So this is the hidden dimension. Define the model, and here is our loss function. Okay, so it's just the binary cross entropy, which is our reconstruction loss, and there's one more KL divergence loss. So here what we are trying to enforce is we want the distribution to be close to unit unit variance and zero mean. So to impose that, we have this KL divergence now. Okay, so when you assume normal Gaussian and so this is just cable divergence. So if you go through the maths, input write down the equation for cable divergence and input these two distributions. Okay, one is the unit standard deviation and zero mean, and the Gaussian distribution with this variance and mean. So you'll end up with this. So when you simplify all that, we'll get this term. Okay. So again, yeah, we'll use the same procedure. We'll define a optimizer, learning rate, and yeah, we'll run this for 30 epochs. So what we are doing is we are taking this image X, okay, we resizing it because we saw the size of the image was, you look at the data set. It was this, right? One cross. So we'll flatten this out. Okay. So for that, yeah, so in the data loader we saw we were getting 100 cross 1 cross 28 cross 28. So if you look at that, yeah. So we want to flatten this out and XD. So what we're doing here is we're just resizing this into a matrix. So we'll get 100 cross 7 84 size matrix. Okay, we'll have to do this grad dot zero. Okay, yeah, initialize all the gradient to 0. Okay, and then pass x through the model, get this x hat, mean and log variance. Okay, and then pass it through the loss function to get the loss, and yeah, we'll do backward pass and the optimization step. So this is the normal STD that we are doing here. Okay, so let me run this. So I'm not using any GPU right now. Yeah, I'm just running this on my local laptop, so it'll be a little slower. Yeah, so it'll take 3 minutes. Okay, so after that, what we'll do is we'll take the decoder of the network and then start with some random noise and we'll see what is the output. Okay, so what we'll be able to do is from random noise we'll be able to generate like an image. And with different noises, we'll get different types of images. So the state of the models that you see, which are stable diffusion models, so so they are based on this principle itself of modeling the distribution. Okay, but they do in like multiple steps. Uh, yeah, but yeah, so diffusion models which came, which was developed from this itself. Like, so while generating the image, we are not conditioning it. So we are giving it just randomness, it will generate. So, but there are ways as well where we can incorporate like additional information, like text information, so that we can give guidance in what is generated. But here we'll just do, yeah, unguided generation. Yeah, any questions that you have? I'll be sharing this notebook so you can go through the code yourself, run everything.
So is it compulsory to give exam or we can get a participation certificate?
Okay, so I have no idea about that. So you will have to, yeah, it's better if you ask the NPTEL support group.
I saw on website. So
Okay, so what was mentioned there? Ki, is taking
nothing
exam
they that.
compulsory
No, not
to get the
compulsory. They can.
certificate?
Uh,
Okay, so I have no idea. It's better if you ask them.
so who can able to answer?
The support group, NPTEL support is there now, or in the discussion forum. So there's a discussion forum for this course. So you can go there and post your queries.
Okay, sir.
Yeah, and the support team is quite active, so yeah, they'll respond to you quickly. Okay, so the model is trained now. Okay, so yeah. So what I'm doing here is, yeah, so I'm putting the model in eval mode. Uh, this is not required for our model. Okay. So when we are using dropout and all, yeah, so for that, because the test time and the train time behavior would be different. So for that and all, we can use this, but for R, it won't make that difference. Okay, so what I'm doing here is I'm just taking the test data loader, taking an image from the data loader, okay, and passing through the entire model. Okay, so input is image, it'll go through the decoder and so basically just to get a feel key what is happening. So yeah, so I have this. Okay, so the input image was, let's see what the input image is. Okay, so it's a one zero mix. Okay, so there are many inputs. So we are passing a batch through it. So yeah, this is one of the images from the batch. But here, yeah. So we can index. So I've written a function where you can index and see what is happening. So let us see what the 10th input and output is. Okay, so this was what we gave as input to the model and again reconstructed it back. Okay, so that is what is expected from the model, but this is not that interesting. So interesting part is over here. So what we are doing is we are taking random noise, okay, and passing that through the, we have just taken out the decoder part. Okay, so so this is the decoder. Yeah, we are initializing the latent from with a random noise and just passing the random noise through the model. And let's see what we get as output. Okay, let's do this and yeah. So we given this random input and you see it has recovered 8. Okay. So this is how this autoencoders could be used as a generative model. You're starting with a random noise and predicting image out of it. So let's look at other examples as well. So here it has generated 0. Here it has generated 8 from random noise. Okay. So yeah. So basically the latest model that you're seeing like stable diffusion and all are all built on the math and concepts which are in this variational autoencoders. Okay, so yeah, these are some of the like basic foundations and diffusion models and all are built on this. Yeah, so it's yeah, we are out of time, so it's already 9:10. Yeah, we'll stop here. Any queries? Uh, any questions or queries? Yeah, I'll be sharing all the notebooks. I think this notebook I have already uploaded before the session. So you could have like run the code along with me to get a better feel of what is happening. But yeah. So are there any questions? I can see drive link. Okay. And like I'll show you how to navigate. So you have to, if you go to the course web page. Okay. So is my screen is visible, right?
Yes, yes, sir.
Okay. So if you so over here in the bottom, there's this problem solving session tab. Okay. And here, I guess if you go to this link, yeah. So if you press here, press this link, you'll redirect to this Google Sheet. Okay. So here, so I'm Suchit Prabhu. So over here, I've kept all the documents, all the notebooks and slides. I uploaded after the. So you can get the link to the video lecture over here, and then yeah, in this drive you'll get all the slides and notebook. So the autoencoder part I had uploaded, you could have like directly opened it in Colab and start. Could have run the code along with me. Yeah, so this is how you can access all the notebooks. Yeah, so yeah, let us end the session over here. Okay, thank you for attending, guys. Bye.